This is EE300 Linear Circuit Analysis 2, Module 2, Video 2, Exponential Inputs. In this video, we'll review previous work on network functions. We'll look at an example circuit to derive some network functions. We'll look at the special case of exponential inputs to linear circuits, and then we'll do a summary and preview of coming attractions. Review. Previously, we found that the concept of the network function, which was a zero-state response attribute of circuits. In the zero state, it's the ratio of the S-domain output to the S-domain input. And by zero state, we mean there's no initial conditions. Our inputs are of the form 0 for t less than 0, so there is no stored energy in the circuit at t equals 0. And when we do circuit analysis in those cases, we don't have to use the initial condition sources on capacitors and inductors. It simplifies our world. When we look at the ratio of the output voltage in the S-domain, the voltage in the S-domain to the current in the S-domain at a terminal pair, particularly the same terminal pair, we call that a driving point impedance. When it's current over voltage at the terminal pair, we call that a driving point admittance. And when we're looking at a transfer function, which is the ratio of an output branch variable at one terminal pair relative to an input branch variable at another terminal pair, we call that a transfer function. But we also will just call it the system function or the network function, even though formally impedances and admittances at the driving points are also system functions and network functions. Let's look at an example. Here's the series RC circuit. The input is V1 of t, a driving voltage source. The output is the voltage across the resistor R, but we also have the current at the driving point at the input, I1 of t. Let's find the input admittance, the driving point input admittance, and the impedance at the same place, and then also the transfer function V2 of S over V1 of S. First, the admittance. To find the admittance, we divide the input voltage by the series resistance of the capacitance in series with the resistor. That's just R plus 1 over SC. And then we do our standard processing here, where first we want to clear out the compound fraction by multiplying through by SC over SC, and then we want to get a leading coefficient of 1, so we divide by RC over RC. And so the admittance turns out to be 1 over R times all of S over S plus 1 over RC. The impedance then is the arithmetic inverse of that, so that's R over S plus 1 over RC over S. The poles of the admittance are the zeros of the impedance. The zeros of the admittance are the poles of the impedance. This is it, as long as it's at the same port, the same terminal pair. For the network function, we'd use the voltage divider, so we have R over the series impedance R plus 1 over SC times the input voltage. Again, multiply by SC over SC, divide by 1 over SC over 1 over SC, or multiply by 1 over SC 1 over RC over 1 over RC to get the leading coefficient of 1, and then take V1 of S to the other side to get the transfer function S over S plus 1 over RC. Let's put some component values in here. Say you have a 1 k ohm resistor and a 1 microfarad capacitor. Then the admittance is 0.001 S over S plus 1,000 mhos or Siemens. The impedance is 1,000 S plus 1,000 over S ohms, and the transfer function is S over S plus 1,000. Now let's consider the case of exponential inputs. Let's first work an example using the previous circuit. Let's suppose the input is 9 e to the minus 100t u of t. So to find the output, we multiply the transfer function times the S-domain input. That gives us the output in the S-domain, then we can inverse transform. So the transfer function was S over S plus 1,000. The input in the S-domain is 9, that's the amplitude, over S plus 100. That's the transform of e to the minus 100t. And we can do our partial fractions. It's going to be something over S plus 100. That something turns out to be minus 1. Plus something over S plus 1,000. That something turns out to be 10. So when we inverse transform, we have minus e to the minus 100t plus 10 e to the minus 1,000t u of t. There's an input pole at minus 100. The exponential input exponential has a rate minus 100. So the force component of the output is going to be an exponential with a rate of minus 100 also, just by Laplace. And that's got a time constant of 10 milliseconds. The pole in the circuit, associated with the circuit from the RC, has a rate of minus 1,000. So there's going to be an exponential in the output with a rate of minus 1,000. That's got a time constant of 1 millisecond. When we look at how this all puts together graphically, the blue line here is the natural response, 10 e to the minus 1,000 t. The red line is the forced response, minus 1 e to the minus 100 t. So even though the natural response has a bigger response in the output, 10 volts compared to minus 1 volts, the rate of the natural response is faster, the time constant is shorter than the forced responses. So in the long run, the output looks like the forced response. You can see the first 5 milliseconds, you see the natural response, but that goes to 0, so that after that time and over the rest of the 50 milliseconds of the response before the forced response goes away, all you see is forced response. That's going to be a property we're going to exploit in what comes next. So let's consider the broad case of exponentials, e to the s naught t, where s naught can be some number, real or complex. If s naught is minus alpha, we've seen that, that's what we just had, that's a decaying exponential. But if s naught is plus alpha, that's a blowing up exponential. That's really in the realm of possibilities, and that may be useful to us at certain times to have inputs that are blowing up exponentials. In between there is the case of s naught equals 0, a constant. That's what we've had historically, just step responses. Switch changes at t equals 0. Inputs are piecewise constant inputs. For sinusoids, we know we can build cos and sine out of e to the j omega naught t, because e to the j omega naught t is cos omega naught t plus j sine omega naught t. So if we add that to its conjugate, the sine terms cancel out, and we take half of that to get a cosine. Or if we take the difference between e to the j omega naught t and its conjugate, then the cosine terms go away, and we get 2j sine. So to get sine back, we have to divide by 2j to get a real valued sine waveform. So we can build signals of interest out of exponentials. And then let's think about our network function with n distinct poles and m distinct zeros that really ought to say n greater than or equal to m. You can have equality here. We're trying to avoid the case where we have a improper rational function to do the inverse Laplace transform to find the output. So we're going to add a pole when we include our input. So we really need for our network function to be n greater than or equal to m. No more poles than you have zeros. So the exponential input has a frequency s naught, and let's presume it's not at a pole frequency. In the earlier, we presumed they were distinct poles. We'll come back to that in a minute, but for now, let's just assume they are distinct. So if the input frequency is not at a pole frequency, now we have n plus 1 distinct exponentials in the output. But the input's going to be some amplitude cap v naught e to the s naught t u of t. So when we Laplace transform that, we get v naught over s minus s naught. We multiply the transfer function by the input in the s domain to get the output in the s domain. And then we know we can write our answer as partial fractions. So we know we're going to get e to the s naught t, e to the sp1t, e to the sp2t, etc. n plus 1 exponentials in the output. We can find the amplitude of the input term in the output by doing, and all of them actually by doing cover up, but let's just focus on the input term. So we multiply by s minus s naught, evaluated s equals s naught, and when you do that, you get a number. And that number turns out to be the network function evaluated at the input frequency. So all that k, s naught minus sd1, etc., all the way through s naught minus spn is h evaluated at the frequency s naught. So we can say that the amplitude of the input in the output, the input was an e to the s naught t exponential. There's going to be an e to the s naught t exponential in the output, and its amplitude is its own amplitude scaled by h of s naught. The amplitude of the force term in the output is h of s naught, the network function, evaluated at the input frequency, times the input amplitude. So let's go back to our circuit and see what that means. We had a network function of s over s plus 1,000 for the transfer from input v1 of t to output v2 of t. The input was 9 e to the minus 100t, so s naught is minus 100. When we plug that in to h of minus 100 is minus 100 over minus 100 plus 1,000, which is minus 100 over 900, which is minus 1/9. And then the input amplitude was 9, v naught was 9, so the amplitude of e to the minus 100t in the output is minus 1/9 times 9, which is minus 1. The natural response is going to be something times e to the minus 1,000t, but we saw earlier that when the natural pole frequency was bigger and the time constant faster than the input pole frequency, the natural response goes away and we're just left with the forced response. So that's why we start to focus on this, being able to say h of s naught and look at the forced response, because in the long run, the forced response is going to matter more than the natural response very frequently. So as long as the input frequency is not a pole frequency, the output is going to have the form h of s naught, that's a number, times v naught, e to the s naught t. So the amplitude of the input exponential in the output is going to be h of s naught v naught, plus the natural response terms, k1 e to the s1t all the way up to k sub n e to the s sub nt. We say that the exponentials are eigenfunctions of linear circuits. That's a $10 word. It means they repeat themselves in the output. You may have seen it in linear algebra where you have eigenvectors. You have a vector pointing in one direction is your input, and you have a vector in the same direction or flipped. Possibly you have it in the output. That means you have exponentials with the rate s naught in the input. You get an exponential in the output with the same rate, and that scale factor h of s naught is what's called the eigenvalue for the circuit, just like you had eigenvalues in linear algebra. As long as the natural frequencies have faster rates, faster time constants than the input does, the natural response is going to go away before the forced will. So if you wait long enough, that's what all that limit t goes to infinity means there. If you waited long enough, the natural response goes away and you're just left with h of s naught v naught e to the s naught t as the response. And that's going to be the case as long as all your poles are in the left-hand side of the S-plane and you're dealing with step inputs and sinusoidal inputs. In those cases, the long run, you're going to get a steady state response, either the DC response to the step or the sinusoidal response to the sinusoid. And of course, we're going to look at more of that in more detail later. If your input frequency is a pole frequency, then you can't use the system function concept. You can't say h of s naught anymore, because you're going to have your exponential input, and you're going to have t times the exponential input, etc., up to the number of poles you have there. And it turned out that the restriction on distinct poles didn't matter, because if you had repeated poles, then you would just have pole frequency exponential, t, pole frequency exponential, etc. Something to think about. We'll come back to in a video in the near future discussing poles and zeros is what happens if your input's at a zero, at the frequency of a zero. What's h of s naught when s naught is a zero? So to summarize and give a future look here, we saw today that when the input to the circuit is an exponential of rate s naught and amplitude v naught, and there's no poles in the circuit at s naught, the output includes an exponential of rate s naught, amplitude h of s naught, v naught. The output amplitude of the input the exponential at the input frequency is h evaluated at the input frequency times v naught. We say that exponentials are eigenfunctions of linear circuits, and h of s evaluated at the input frequency is the eigenvalue. And as long as the input rate is slower than the pole rates, then the output's going to look like the input in the long run. And again, we'll exploit that when we put steps in and get constants out in the long run. And we put sinusoids in and we get sinusoids out at the same frequency in the long run. What we're going to look at next is being able to go from the network function to the input-output differential equation. And again, more about what these poles and zeros mean for the input-output behavior, we'll be able to make some pretty broad statements about where the poles show up, what the inputs do, zeros do, and how to think about them, not only in terms of the network function, but also in terms of the parameters of the differential equation. So this has been EE300 Linear Circuit Analysis 2, Module 2, Video 2, Exponential Inputs.